Hey, welcome back. Here with an example on current division using parallel resistors. So what we want to do is we want to find the current flowing through each of the resistors and the whole circuit in general in this problem. So to get started, what we need to do is we need to figure out the equivalent or total resistance of the whole circuit. And the expression from that is just R tot is just equal to 1 over the inverse of each of them. So R1 plus 1 over R2 plus 1 over R3. Now we actually know what the individual resistances are because they're labeled here, so let's actually just update this so we have 1 over 10 ohms, 1 over 20 ohms, and 1 over 30 ohms. So if you just crunch this in the calculator, we're going to get 1 over 0.1833, and that reduces to our total to be 5.45 ohms. So that's the total resistance or equivalent resistance of these three parallel resistors. And then what we can do is we can apply Ohm's law. So we have V equals IR, and we can rearrange. So we have I is equal to V over R. In this case, we're looking at I total and R total. Now the voltage drop from this side to this side is going to be 3 volts. So we can put that in as 3 volts over 5.45 ohms, and that gives us a value of our total current of 0.55 amps. So that is the amount of current that's flowing out of the voltage source. Right here we can label it on as I tot is equal to 0.55 amps, and that's the same amount that's coming in here. Then we can label on each of the unknown currents. So let's call this I1, I2, and I3. Now the next thing that we can do is we can write the current divider formula, which is the individual current of the resistor we're looking at is equal to the total current times the ratio of the total resistance over the individual resistance of each resistor. And if you can't remember that, or you're asked to prove kind of why it is, you can write Ohm's law. We have I equals V over R. And we can give the subscript here for the individual resistor that we're looking at, with this being the voltage drop across from this side to this side. But that's also the same as the voltage drop from here to here when we're using a total resistance. So this V here is the same as this V. And what we can do is we can plug in this IR, which already has the subscripts from the little step below, which was total current and total resistance. So we can update that. So we have the individual current through one resistor is equal to V, which is I tot times R tot over Ri. This whole thing is over Ri. But you can see that we can pretty much just have I tot times R tot over Ri, which is what we have here. Sometimes this is like the more common way that you see the current division formula. So anyways, let's erase this rough work, but it's there in case you needed to see how we get this. And then we can plug in the values that we have. So I tot is equal to 0.55 amps. Let's put this all in brackets and multiply it by this ratio where we have our total on the top, so that's 5.45 ohms. And let's plug in resistor 1 here, so that is the 10 ohm resistor. And we can write I1, maybe let's just label these on to be super clear. This is R1, this is R2, and this is R3. So I1 is just equal to 0.55 times 5.45 divided by 10, and that gives us a value of 0.30 amps. For resistor 2, we can just come in here and update this value, so we're going to have 20 ohms on the bottom, and then we can do the same calculation, and we're going to find that I2 is equal to 0.15 amps. And then we can repeat it one last time. So for resistor 3, if we just update this to 30 ohms, then the current flowing through resistor 3 is going to be 0.10 amps. And again, that's just 0.55 amps times 5.45 ohms divided by 30 ohms. And one last thing to realize here is when we look at these, if you take the sum of I1, I2, and I3, it just adds up to 0.55 amps. And that's saying that we have 0.55 amps flowing in here, and then a sum of 0.55 coming through these three branches, and then back here again. So the total current in equals the total current out, and everything checks out according to Kirchhoffs' current law. So yeah, that's it for this quick video, and join me in the next video and we'll go over one more current division example problem with some more parallel resistors.